Okay, this is a screencast 4, assignment 7.2, use of Lagrange mechanics to model an interesting system numerically. And in this case, I have modeled an motion of ice cube in a sphere. First, the coordinate that is required to model the system is only theta, because theta is sufficient enough to state any position of ice cube at any time. So our first Lagrange function is going to be t minus u, and the kinetic energy in terms of thetas are going to be 1 by 2 mr squared cosine square theta dot square plus 1 by 2 mr square sine square theta dot square. And similarly, the potential energy is mgr cosine theta. And now this is the partial of L with respect to theta, partial of L with respect to theta dot, and this is the time derivative of partial of L with respect to theta dot. And then using the Lagrange mechanics, the differential equation I need to model the motion of ice cube in a sphere is g sine theta equals to r theta dot. Now this differential equation actually tells me the motion of ice cube in a sphere, but this is not complete, because this differential equation tells me the circular motion around the sphere, which is not true, because at some point the ice cube will be leaving off the sphere. So in order to know at which point it leaves off the sphere, now I have used simple mechanics over here. First of all, I'm trying to find the final velocity at which it leaves off the sphere, so which I can simply find by using the conservation of energy. And the final velocity is going to be this expression over here. Now to find the height, to find the height, first of all, in circular motion, mg cosine theta minus normal force is equals to mv squared by r. And I can use the velocity from the expression over here, and if I use these two equations. And also one more thing, when the ice cube leaps off the spherical surface, the normal force is going to be 0. So using these three things, I can find the height at which the ice cube leaps off the sphere. So which is going to be, there's a slight mistake over here. This g should not be here, because this and this g cancels and then the g goes away. So the height at which this ice cube leaps off the sphere is going to be 2 times its radius by 3 plus 1/3 of initial velocity square over z. And using these equations, now I can model the motion of ice cube in a sphere, which I have successfully done in BPython. This is the model in BPython. Okay, this portion in while loop over here, it shows the motion of ice cube within the sphere. That means it is up to the point at which the ice cube leaps off the sphere, and this portion describes the motion after it leaves the ice cube leaves the sphere, which would be projectile. Let me run it and then show you. Okay, as you can see, it is spherical, and then it leaps off at this point, and then the motion is then projectile, since gravity is the only force acting after that point. And this arrow shows the gravitational force, whereas this arrow is the normal force, and this is the point at which normal force becomes 0. The scale of this arrow is not, these arrows not up to scale, these are just for the direction. And yeah, and one more thing about the angle at which the ice cube leaves the surface, which is over here. This is the angle. It is in terms of radian, 0.8487, and the degree equivalent of that is 48.62 degrees. So that's it.